Start PCA now, and before starting PCA, actually, I usually start with this topic called as variance, covariance, and covariance matrix. So why we are studying these two three terminology before? We have seen this terminology before also, I suppose. But again, we will be seeing these terminologies because PCA is based on this, and your PCA algorithm, PCA learning algorithm uses these terminologies in order to find out whatever learning it has to find. Okay, so it is very important to understand what is variance, what is covariance, and what is covariance matrix, because when we will see PCA, these terminologies will often be used there, will be, I mean, more often be used. So at that time we should be clear about what is these things. Okay, so I have just prepared two three slides for that. This we will see that. Okay, now
Okay.
let us see first thing. So maybe you can see this data. So this is variance. So you have say five dogs whose heights are given 60, 47, 17, 43, and 30. So how do we calculate mean? We calculate mean by simply taking the average. Then what is variance? Variance is
Difference.
what is variance? Variance is each data point minus the mean and squared and
Square.
summed up over and 1 by n, the number of data point. This is number of data point, which is actually this, and this terminology is basically these. Each data point minus their mean 39, and then you have summed it over. So this sum is there, right? Here is sum. All these square terminologies are summed up, right? You can see here. So basically this is called variance. So this is variance, okay? This is mean, this is variance. Standard deviation is under root of that this we already know. Now here if you see, the data is one dimensional. The data whatever you see, the height of the dog, that is just a 1D, one value is there, right? It's not like a 2D or 3D. So data is one dimensional. Now we will see the covariance. So covariance, when you are talking about covariance, means your data is more than one dimension. It means your data is at least 2D or at least 3D. Okay. If you are talking about covariance, it means your data is more than one dimensional. So when I say more than one dimensional, it means what? See, here your x is the data. This is basically the data. X is data. If you see this data, it's a three-dimensional data points are there. How many dimension? Three
Three
dimensional.
dimension.
It has three dimension: x1, x2, x3. Three dimensions. Now, if someone says that what is the mean of this data, so it's simple. You just calculate the mean of this, and this average, and you will write the mean value 4.1, 2.08, and 0.6. This value, right? So this is the mean. Now suppose if somebody will say that what is the variance? Now tell me first of all, variance as we know is this,
Sum of n.
but But here is a but. The but is there x was one value earlier, mean was one value, but now my x is a three-dimensional data and my mean is also three-dimensional data. So how will I minus it? How will I minus and sum it over? Like it is not possible, right? With variance. One way, one way is that you calculated the mean. Now I will calculate the variance like this. Variance I will calculate like this. 4 minus 4.1 plus 4.2 minus 4.1 plus 3.9 minus 4.1 plus 4.3 minus 4.1. Right? Are you understanding? This, and finally 4.1 minus 4.1, this, and then I did this divided by 5. Summed it over, squared, summed it over and divided by 5. Like this, if I will calculate the variance, it will calculate the variance of first dimension only, isn't it?
Yes.
And independently you can calculate for second dimension, and independently you can calculate the variance for third dimension also. Are you understanding this? Like we calculate the variance of one dimension, I can calculate the variance of all these 3 or 10 or 20 dimension, whatever it is, independently. How? Independently.
Yes.
Independently I can calculate, like then my variance will also be, like in this case my variance will also be a 3-dimension data. One dimension for this, one value of variance for this, and the third one for this. Okay, so that is the variance. But what we want is, we want that it is not only that we have to independently calculate the variance, that of course you will do, but also we have to calculate the variance of one axis with the other, one dimension with the other dimension. We also have to see what is variance after all. What is the physical significance of variance? Variance is
Right.
basically signifies the spread, right? So if I talk
Yeah.
about this, it is like 4.1 is in the middle, and then you have 4.3, you have 3.9, you have 4.2 somewhere, you have 4 somewhere, right? So it is like this is the mid value and these are the spread points, right? So variance tells about the spread. It tells about how spread, how wide your data distribution is and all those things, right? So, but in covariance, what do we want? That what is the variance in this data along, I mean, depending on this data also. So the formula of variance, if you see, was this, right? This formula,
Okay.
I can also write something like this. This is a squared, right? So basically this is like this, a squared thing. This, I can write this a minus b whole square equal like this also, no? A minus b into a minus b. So I have expanded it. Now covariance says that my one dimension will be x. One dimension will be this one first, but I want to check the covariance between first and second dimension. So then second dimension will be y. So y. mean of y, and this is mean of x. And then you have to divide it by n. So this expansion, one term will be now yth term. So this is covariance between 1 and 2. Like you can calculate covariance between 1 and 2, covariance between 2 and 3, covariance between 1 and 3.
One and
You can calculate between these, right?
yes, yes.
So the covariance formula is this. If you see the covariance formula, this is the covariance formula. You have to take first xi minus x mean, then yi, then y mean, this one. And this is the covariance between 1 and 2 only. Similarly, you can calculate 1, 3, then maybe 2, 3, like this. So, in total, if you see the covariance matrix, the covariance if you calculate, covariance will become a matrix. How? First, you calculate the covariance between 1 and 1. Means the independent variance of this. Independent variance. You understood what I mean by independent variance? Independent variance.
Yeah. Variance of first.
Yeah, first only squared. Then you calculate first and second, like this one and this one, putting it in this formula. This one from this and this one from this. Then you calculate first and third. Then you calculate second and one, which will be same as this. Exactly same. Values will come same. Then second independently. This one. Independently. Then second and third. These two. Then 3 and 1,
Third and
which will be similar to this one. Then 3 and 2, which will be similar to this one. And then 3 and 3. 3 and 3 will be independent this. So you will get a matrix which is called as covariance matrix. And this matrix is a symmetric matrix. Symmetric matrix means these values will be same as these values. See, the covariance of 1 to 2 will be same as covariance of 2 to 1. Na? The values, even if you exchange the dimension, the subtract and the squaring and those things is going to come same. Na?
okay.
The values are going to be same. Exactly. So it's a symmetric matrix. Symmetric matrix means I and J are always same. Okay.
Okay.
So you understood covariance matrix?
Yes, yes.
Huh?
Yes, yes, yes.
So that is the funda, okay. So anyway, so see, how can you see this calculation?
So it is always in matrix format.
Yeah, covariance. See, if your data is say of 10 dimension, so say 500 data points are there into 10 dimension. Your covariance matrix will always be 10 into 10. Because like first ka second, Then I mean first
Mm-hmm.
and third, first and fourth, first with 10, then second with 1, second with second, second with 3, second with 4. So covariance matrix has always to do with the number of dimensions. Okay.
Okay. Okay.
Uh, you understood, na?
Mm-hmm.
This covariance matrix has always to do with dimension. Whatever the number of dimension will be, the same square matrix of same dimension covariance matrix will be. Okay. So can you see the calculation over here?
Mm-hmm. Yes.
This one. See, this is like calculating the covariance between feature 1 and feature 3. This one and this one. Okay. You see this one. So how will you calculate it? 4 minus
4.
4.1. Okay, you just try to understand. I will come in a second.
Okay.
Yeah. Yeah, hello.
Yeah, yeah.
Yeah, see,
Yes.
this is like see covariance between feature 1 and 3. So 4 minus this one plus 4.2 minus this one, 3.9 minus this one, 4.3, then this. Then 0.6 minus this one, 5.9 this one, this one, this one, this one. Right?
Okay.
So it goes like that, and then you calculate, and then um,
Why divide by 4? It should be
yeah,
5, no?
divide by 4. Divide by 4 or divide by 5, anything. This n, some people use n minus 1, some people use n.
Okay.
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 Anyway, so that's how you calculate the covariance matrix. Okay. Now you see this covariance matrix. This is the x. What is the number of dimension here in x?
3. 3 dimension. X or S?
3 dimension x. So what will be the s? S is covariance matrix.
Okay.
So what is s?
Hmm.
S is 3 into 3,
3.
right? So that's what I have told you. No? Whatever be the number of dimension, the same dimension, the square matrix of same dimension will be made.
Okay. Okay.
Okay.
So if there are 4 dimension, then it could be 4 dimension
4 into
covariance
4. 4
matrix.
into 4.
4 into 4. 4 into 4. Okay. Yes. Okay.
Okay. So that is it. That is it. That's what I was just wanted to tell you, that this is how you calculate the variance, and you as I have told you earlier also, this is the Gaussian. This is called the mean, and this is called the
Hmm.
variance.
Very.
Okay. So if the data distribution is like this, I will show you in fact in more specific way maybe. See, uh, let us say the data is like this.
Okay.
Now this data distribution has more variance, or this data distribution has more variance.
First one has more variance.
First one has more variance because if I fit a Gaussian over here, this will be more thick, and if I fit a Gaussian over here, this will be thin. So the mean will lie here. For this, the mean will lie here, but this distance will be more thicker. I mean, the spread is more. Here, the spread is less. Okay.
Yes.
So that actually physically you mean this thing. Okay.
Mm-hmm. Okay. So we talk about mean square error.
Yeah. It's
Uh, is the difference?
mean
What is
mean
how is
squared. Yeah, mean squared error is between the actual value and predicted value.
predicted value? Yeah, predicted
Squared
value.
over, summed over, and
Some.
so and
Mhm.
variance is x value minus mean value squared over n. So if you ask me, there is no difference. Only thing is the application is different. Mean squared error is used when you have to find the error between the actual and the predicted value. Here there is in data distribution, in statistics, it is not like actual and predicted. It is like you have some data and the mean of the data is from that you have to do this variance calculation. But yeah, in that sense, if you ask me, both are L2 norm, both are in the
Mhm.
square form, both are the difference, square difference. So that way both are same.
Okay. So only predicted value is present in the mean square error.
Yeah, the context is different, right? The context is totally different, na?
Yeah, yeah.
When do I use mean squared error? Mean squared error I will use in that context where I have some actual values and I am predicting some values, and then I am calculating the loss. I am calculating the error.
Hmm.
There I calculate this L2 norm of the values, the predicted and the actual values, and call it as mean squared error. Here the context is totally different. I am trying to find out the spread in the data. I'm not predicting anything. I have just data distribution and I want to know the characteristic of that data distribution, that how much spread is there in the data. So the contexts are different.
Okay.
Okay.
Okay. Okay.
So basically that's what I just wanted to tell you about this mean and variance stuff, because these things will come in PCA. So now maybe we will start this PCA. Okay.
Okay.
Okay. So first of all, you need to understand what is PCA and why PCA, why it is actually used. I mean, what is the motive behind using it? Okay. And other than that, um, this we will see the steps, we will see the measure, we will see the algorithm how to calculate PCA, and finally maybe a Python implementation on some data set. Okay. So let us start with
Okay.
dimensionality reduction PCA technique. So majorly PCA, which is also called as principal component analysis. Okay. So this principal component analysis is a dimensionality reduction technique. Now, what is this dimensionality reduction technique? I will try to explain. So, suppose your data has like iris dataset. Suppose you take iris dataset. Iris dataset, you remember, na? Setosa, Versica,
Yes, Appleton.
Versica, three types of flower. How many features were there?
Zeppelin, petal length, four features.
Four features, right? So and let's say 100 values were there, 100 data points. So 100 data point into four. This was
Into
my
four.
data set, right?
Yes.
So four features: sepal length, sepal width,
Petal,
petal length.
petal length, petal.
So what PCA says, PCA is a dimensionality reduction technique. So it says, can we reduce the dimension 100 into 4 into, let us say, 100 into 2. So this is a very vague example. You just try to maybe visualize a scenario where you have, let's say, 100 dimensions, and in 100 dimensions now you want to reduce it to maybe 30 dimension. So can you represent your features, 100 features, into 30 new features? I am saying, if your data is 100 dimension, can you change it to 30 dimension? Now you will say, yeah, we can, you may think that we can do that by removing 70 dimensions. From this, the unnecessary 70 dimension I will remove, and I will only keep the useful 30. That you may think, that one may think, but PCA does not believe in losing information. PCA does not want that you lose 70 features. The concept of PCA is, you don't need to remove the feature, but you need to transform your features such that the whatever information you are representing in 100 dimension, if I can represent the same information in only 30 dimension. Understood?
Okay.
I
Okay.
will give you an example. What PCA says is, let us say you have sepal length, sepal width, petal length, and petal width. 4 features. Now, can I make 2 features, say x1 and x2, which these, can I make 2 features which is representation of these 4 features? It's not like I am removing any 2 and I am keeping the rest 2 here. No, it's not like that. It is not like that. Okay. What actually it is, sepal length, sepal width, petal width, and then it will give you, say, x1 and x2. So it actually means that let x1 be some linear transformation, linear combination of these features. Say, let's say 0.4 SL sepal length plus, say, 0.8 sepal width plus, zero point 0.3 petal length, and say plus 1 petal width.
Yeah.
Some linear combination of the features, and x2 let it be, say, 0.6 sepal length, 0.2 sepal width, and let's say 0.7 petal length, and no petal width, just like that only. So somehow you are representing your 4 features into 2 features only, right?
Yeah.
Isn't it?
Yes.
So that is what I am saying. This is one of this data. So basically, you understood now what PCA does in a overview scenario. Like as an overview, you should understand what PCA does. I will go into details. I will talk about this a lot. I mean, PCA is a little mathematical and a little complex topic. So we will go maybe seeing examples. But what I try to make you understand is like what actually PCA represents. PCA simply means that you are transforming your data from existing features to create some new features which represents the same information in that of the data, but with less number of features. Are you getting my point? PCA is a linear transformation which transforms the data points with D dimension into the data points in L dimension, where L is smaller than D. Okay.
Okay.
So if you have a 100 dimension feature, can you reduce those features into 10 dimension? That thing PCA does. Can you find out new 10 features which is some combination of those 100 features only, right? So like that, PCA basically is a dimension. Now the question: why do you need dimensionality reduction? Why do you want on the first hand only? Why do you want to suppress the data, the features? Why do you want to reduce the number of features? I will tell
To
you
avoid complexity.
what.
To avoid complexity,
Yeah, 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 yeah.
calculation,
Of
calculation,
course,
and yeah.
of course. So there are two, three things actually. I will tell you.
Mhm.
So one thing is sometime to avoid the complexity, or you can say to avoid the computation, unnecessary computation. Like, see, where PCA is used, PCA is used a lot in image processing. And why image processing, I will tell you. The number of features in image processing is like in tens of thousands. Say how? Even if you have a small image of 100 into 100 pixels, 100 into 100 pixels, even if you have 100 into 100 pixel image, if you will flatten it, if you will look it as a vector, 100 into 100 means 10,000 pixels you are carrying, and 10,000, each pixel is a feature. So in image processing at that time you will have 10,000 features. Are you getting my point? So
Yes.
10,000 features are like huge. And for any machine learning algorithm, when you will apply maybe support vector machine, or any other maybe random forest or whatever it is, when you apply that 10,000 with 10,000 pixels, those are features. The computation becomes slow and it becomes a complex thing to train. The training itself will cost you a lot. So sometimes to fasten the computation, if those 10,000 pixels can be represented by say 100 dimensions only, suppose whatever information is there in 10,000 pixels, suppose if I
Mhm.
can represent that 10,000 uh, pixels into just 100 values, if I can reduce, so then the computation of that will be whatever application, the whatever support vector machine training or whatever training I am doing, that will become fast, because earlier your SVM has to deal with a 10,000 dimensional data. Now your SVM has to deal with only 10 dimensional data. So the idea is, if you can transform your good number of features, if you want to say, if you can transform your huge amount of features into a smaller number of features, we must do that in order to fasten the computation. But now here is an important thing. When you transform from 100 dimension to 30 dimension, or 100 dimension to 10 dimension, you remember there is nothing like that 100 dimension, whatever information are there in 10,000 pixels, that you can exactly um, put in just 100 values. No, 10,000 pixels cannot be put in 100. So what I am trying to say, there will be some loss. definitely there will be some loss. When you apply PCA and you are trying to reduce your uh, you are trying to reduce the number of features, the dimensionality,
Mm.
you so that's what I am telling. If you are trying to reduce the number of features, you are certain to lose some information. Are you getting my point? So,
Yes.
but the thing is, PCA takes care of this thing that the information lost is very less, as little as possible. It so if you are reducing from 100 dimension to 10 dimension by retaining 96% of variance, just try to understand my statement. We will discuss about it. We will discuss. Right now, I am just telling you things. We will go when we will go slide by slide. We will see things. What I am trying to say is, if I say that I am reducing from 100 dimensional data to 10 dimensional data, and also retaining 96% of variance, it means that 96% of the information I am keeping, 4% I am losing by reducing 100 dimension to 10 dimension. Are you getting my point?
Yeah.
Yeah. So, of course, there is some loss, but that loss PCA is, proposed, the PCA algorithm is such that it reduces in a way that the loss occurred is, the information loss is as little as possible. Okay.
Okay.
Now, what is the motivation? So first motivation is data compression. This you can easily see by whatever discussion we had now. I have
Mm.
repetitively told that you have say 1,000 of images of 100 by 100. So you have 1,000 images of 10, each having 10,000 pixels, 100 by 100, and you have 1,000 images each having 10,000 pixels. So when you those 10,000 pixels are just reduced into 100, then you have thousands of images of just 100 values, each having 100 values. So the data is compressed. So sometime in image processing only, the for data compression, PCA is very much used, and PCA is also famous for that, for data compression. So basically, 1,000 images into say 1,000 images of 100 into 100. So let us say 1,000 images into 10,000 pixels, 100 into 100. Hmm.
Mm.
So 1,000 into 10,000, 1,000 into 10,000. This can be reduced to 1,000 images into say 10,000. You can represent in say 100. So now this is less or this is less? This is na almost by
Yes.
the factor of 100. You have reduced the data size because it was 100 images with 10,000 pixels, 1,000 images with 10,000 pixels. Now here you have 1,000 images with only 100 pixels. Got it? So data compression is one of the motivation. Another motivation I will tell you, a very uh, you can I mean very direct motivation, direct benefit basically. Uh, we know that we can at most visualize till three-dimensional data, right? Now ideally
Yeah.
four-dimensional data. IDC is a four-dimensional data. Or you can have lots of data set where the number of dimensions are very high, maybe 40, 50, 80, 100. There are lots many dimension data. But you can visualize your data till 3D only. So another motivation of PCA comes into play where PCA tries to reduce the dimensionality of data from say 80 or whatever it is to maybe a three-dimensional data. So if you have, say, let us take the example of iris only. If you have four-dimensional data, can you visualize it? No,
No.
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 You cannot visualize a four-dimensional data. Now, if let us suppose I say that you apply PCA and the same iris you transform into two dimension, then two dimension you can definitely visualize,
Yes.
isn't it? So
Yes.
yeah, so that is what I am telling. Any amount of any number of dimensions, what happens is sometimes we reduce it to two dimension or three dimensional data and we can visualize it. So the other motivation for this, if you see, the motivation two is what?
Reduce dimension.
Data visualization.
Visualization.
See, how many features are there? Six,
One, six. Six. Yes.
right? Now these six
Yes.
features, basically this matrix, you can apply PCA and you can form a two-dimensional data. Same features are there. I mean, same data for same six countries, six-dimensional data you converted into two-dimensional.
Two dimension.
Now you can visualize this data, right? Because it is in two-dimensional. So
Yes.
visualization becomes easy. Okay.
Okay.
So one
Okay.
motivation is visualization. Another motivation is data compression.
Data comp.
So let us see the slides. See, this is a 2D, right?
Yeah.
So
This.
pilot skills and pilot enjoyment. This is the data, 2D data. Now, how can you reduce this 2D data into 1D? So whatever your data is, you just pass a line through it. Why I am passing a line? I also want to keep all the information. I don't want to lose the information. So when you are reducing from data to 2D to 1D, this line will become like this. See, you fit this line. So now this is 1D,
Okay.
and all your data has been transformed from this to this.
Okay.
Understood? This was 2D. Now this is 1D. Okay.
Okay. Okay.
Now you may say that this is the linear regression. You can
Hmm.
say that this is linear regression. What is the difference between linear regression and this? In linear regression also you fit data, but I will say linear regression is altogether a different formulation. PCA is altogether a different formulation. What here is happening is I could have taken a data like this. See, for this data, I can take an axis like this. I could have taken this axis also, and I could have projected
Mm.
this data here.
Yeah.
Sorry. Shit. Okay. I could have projected data on this dimension also, and then this dimension I would have said like this, and whatever data is projected, I could have mentioned it, right?
Hmm. Yeah.
But that is what the PCA does. Whether this axis is a good axis, this axis is a good axis, this axis is a good axis, or this axis is a good axis. So PCA finds the transformation. Basically, in PCA, what you are doing, you are transforming your data from a higher dimension to a lower dimension. So PCA takes care of that this thing, that whether your dimensions, I mean whatever number of dimensions you are going to get, which axis to choose. So that axis is chosen. I mean in PCA that axis is chosen which has highest variance. Highest variance.
Very.
Okay, tell me if I could have directly chosen this axis. I could have chosen this axis instead of this. I could have chosen x1. But if you project it on x1, see what happens. What I mean to tell you is like this. See, here the difference between these two data is high. The difference between these two data points is large. But if you project on this, they will become small.
Yes. Yes.
Earlier the variance, the spread was long, I mean more, but after projection on x1, the distance has become short because this will be projected here, this will be projected here, so this is short and this is long, right? We want the axis which will retain this variance as maximum as possible. So this is the axis. Now in this axis, this will be projected here only, and this will be projected here. So the distance is still maintained, right? Are you trying to, are you understanding? See, same case here. If you project here and this one here, still you have a clear cut distance. But if you project here, the distance will reduce. Are you getting my point?
Yes. Yes.
See,
Yes.
let us take this axis as example. If you project this here and if you project this here, this is only this much distance, right? But in actual the distance is more.
Yes. Yes.
But if you will take this axis, then it will also get projected here, and this will also get projected. So distance is huge. I mean the same distance is retained. So that axis I have to choose where the distance, the retained distance is same. Got it? That
But
is
it
the
will be
point.
reduced. No?
Yeah, yeah. While
Distance
you
will be
see
reduced
from
on x-axis.
a higher dimension to a lower dimension, you have to choose the axes in such a way that the variance is maximum. The variance returned is
Oh,
maximum. Yeah. You say some.
okay. If I put it in x-axis, so distance would be reduced between the points.
If I put it in x-axis,
Yeah. So distance would be reduced now.
so I don't want to reduce it, na. I mean, I want the
Oh,
dimension to get reduced, The distance I
Okay.
want to retain. The information,
Okay.
whatever there was in original data, that I want to retain.
Mhm. Okay.
Okay.
Okay. So how to retain that information?
By finding that axis
Okay.
where if I project my data, if I transform my data on that axis, the distance between two data points remains the same. If not exactly same, at least maybe 90% same.
Okay. So it would be parallel line to that axis.
Hmm?
It could be parallel line to that axis, so like passing to the all data points.
Okay, like this,
Uh, Parallel line to
like this.
yes.
Yeah, yeah, it can be this also.
Yes.
Yeah, same thing. It can be parallel line also.
Yeah.
You can find this one, this one, this one, this one, this one, like this. Sorry, this one. Only thing
Yeah.
is
So how we
the
did
variance has to be retained. Okay.
how we decide it nearer to x-axis or near to y-axis?
Hmm.
How would you decide that it is nearer
So
to
that
x-axis
is the
or?
that is the PCA algorithm.
Hmm.
We will see
Okay.
step by step PCA algorithm. It's a mathematically little complex algorithm,
Okay.
which
Okay.
that algorithm actually finds those axes, those dimensions.
Okay.
Where to project. So you are asking now who decides whether it will be this
Hmm.
axis or this axis or this axis.
X-axis.
Parallel
Yes.
to it. Which
Yes.
axis we
Yes.
will take. So that is decided by an algorithm. You might have heard about eigenvectors, eigenvalue, eigenvectors. So eigenvectors are like some orthonormal vectors, like 90 degree dimensions are there, like this x1 and x2. So eigenvectors are actually are the axes. So we find the eigenvectors, the best eigenvectors, and the best eigenvectors are our best axes where I can project my data, and the information loss will be minimal.
Okay.
So through eigenvector and those things we will calculate PCA. I will tell you the steps to calculate. Okay.
Okay. Okay.
So that is one thing. Okay. Now let us come down. See, this is another example of a 3D to 2D. Can you see?
Yeah.
Yeah, a 3D to 2D.
2D. Okay.
You see how many
Okay.
dimensions are there?
Three dimension.
Yeah. Now I have
Three
taken a
dimension.
plane like this.
Hmm.
And onto this plane I have projected all my data. See the middle image.
Yeah.
Onto that axis, I have projected my all the data. When you
Yes.
project all the data onto this plane, then you take out that plane. It's a 2D image like in third picture.
Okay.
Okay. So this is like
Okay.
converting a 3D into 2D. Similarly, 4D can be converted into 2D, 5D can be converted into 2D. Only thing is you have to project your data onto some plane. And the plane should be such that it should retain the distance between the data points. Whatever it can. I'm not saying 100% it should retain, but whatever it can, it should retain. All right.
Yeah, yeah.
Now, yeah. Now, moving ahead, this visualization stuff I have told you. Yeah, principal component analysis formulation. This is easy, and like you said, parallel lines can be taken and all. But still, I will follow this example, whatever it is given in the slide. You see, there are 5 data points, right? These data point 5. Now, if you will see, I will take example of two axes. One axis like this, and another axis like this. When I project all these 5 data points on this, you see how they are projected, right? So basically, if you see, they have all come very close, right? On this in this axis. But at the same time, if you take this as an axis, you see the distance between them are retained, right?
Yeah, yes.
So which axis we will choose? We will choose this one.
This one, yeah.
Okay.
Okay.
So this is just I just wanted to show you what. Yeah. So the so basically our problem formulation is like from 2D I have to take it to 3D or from 3D to 2D, right? Okay. So PCA is not linearly regression, it is different from that. Okay. Now dimensionality reduction principal component analysis algorithm we have to study. Okay. So in this principal component analysis algorithm, we have some steps. We have certain steps like pre-processing, then computing the covariance matrix, computing the eigenvector. Then from eigenvector, we will take some axes, the initial axes in which we want to reduce, and then finally you will have this transformed matrices, the transformed data which you can use for further applications. Okay. Now in dimensionality reduction, how you can get back your data from lower dimension to higher dimension, like reverse PCA, how you can do that we will discuss. And then dimensionality reduction, how do you choose the number of component, that we will discuss, and that will be it. Then there are some advices. So this will be it. So what I will suggest, I will start this algorithm part tomorrow. Okay. Right now, what
Okay.
we will do, we will instead see the example of PCA, that how PCA does things. Okay.